Hey everyone, in this video we're going to learn how to write the equation of a parent function that has been scaled and or reflected. Our first example, write the equation in y equals form of the given function after the described transformation has been performed. The parent function is y equals x squared, and the transformation is a vertical stretch by a factor of 7. Okay, so in our notation that means a scaling of 1, 7. Okay, so the vertical stretch means we're changing the y values. So in the equation of our parent function, if we're multiplying the y's by 7, that means we need to divide y by 7 in our equation. Remember, the equation always tells us how to go backwards, how to get from the graph we want to the parent function. Okay, so if I'm putting this in y equals form, I'd have y equals 7x squared. Okay, so we're essentially going in the reverse direction. They're giving us the scale factor, we're putting it back into the equation, and then rewriting it in y equals form. So our next example, y equals the cube root of x, and the transformation is a vertical compression by a factor of 1/2. Okay, so vertical means happening to the y, so we have a scaling of 1/2. Okay, so if we're multiplying the y's by 1/2, in the equation we're dividing y by 1/2, and then cube root of x divided by 1, which we could write, but we don't need to. So in y equals form, we have y equals 1/2 times the cube root of x. So there are our two equations. Same directions. Now our parent function is y equals the square root of x, and the transformation is a horizontal stretch by a factor of 3. So our scale factor is now 3, 1. We're multiplying the x's by 3. So in our equation, we're going to divide x by 3. And we're done. That's already in y equals form. So we don't have any more work to do. Next, we have y equals the absolute value of x, and the transformation is a horizontal compression by a factor of 3/4. So a scale factor of 3/4, 1. Okay, so if we're multiplying x by 3/4, we're dividing x by 3/4 in our equation. So y equals the absolute value of x divided by 3/4. And we don't want to leave it as division of a fraction. So cleaning this up, we would get y equals 4x over 3 inside of the absolute value. So there's our equation. So this really is helpful of bringing everything full circle. We worked in one direction for most of the first two videos, so now we're reversing. We're being given all the information and trying to put it back in the equation. Write the equation y equals form, so same directions, but now the function that we're starting out with is not a parent function. So we're starting out with y equals quantity 5x cubed, and we're reflecting over the y-axis. So if we're reflecting over the y-axis, that means we're negating the x values. So our scale factor would be -1, 1. Okay, so y equals, so y divided by 1, which we don't need, and then the 5 doesn't affect it, we're dividing x by -1. So in another set of parentheses, like that. Now that looks pretty complicated. We can clean that up. X divided by -1 is just -x. So I can write 5 times -x cubed, which I can go one step further and write y equals -5x quantity cubed. And there we have the equation. So they challenged us a little bit by not giving us a parent function, but as long as we're consistent with our method, shouldn't really throw us off too much. Next up, we have y equals -2 times the square root of x, and the transformation is a horizontal compression by a factor of 1/4. So our scale factor is 1/4, 1. Horizontal means it's happening to the x values. So we have y equals -2 square root of, okay, we're going to divide x by 1/4, And we don't like division of a fraction, so we're going to clean that up. Y equals -2 times the square root of 4x. And there we have it. If suppose it was a vertical compression, so let's say it would be y divided by 1/4, when we go to multiply it over, we would just have to do 1/4 times -2. And then just clean that up. Now write the equation of y equals f of x. Okay, so that's our parent function, that's our starting function, after the described transformation has been performed. First one, vertical stretch by a factor of 10 and a reflection over the x-axis. Okay, so vertical stretch by a factor of 10 means we're multiplying the y values by 10. And then if we're reflecting over the x-axis, that means we're going to negate the y values. So we'll make that scale factor -10. So in our equation, we're going to divide y by -10, and we're going to divide x by 1. So I can just write x. So in y equals form, we'd have y equals -10 f of x. Next, we have a horizontal stretch by a factor of 3 and a vertical compression by a factor of 1/2. So we have both types of scaling occurring here. Okay, so horizontal stretch, that's our x factor, so that's 3. And vertical compression, that's our y factor, so that's 1/2. So in our equation, we're going to divide y by 1/2, and we're going to divide x by 3. And putting in y equals form, we'd have y equals 1/2 f of x over 3. Perfect. Next example, we have to do a bit of thinking. Base your answers on the function y equals x divided by 2 quantity cubed. For the following function, state a horizontal scaling that occurred to the parent function. So our scale factor, x divided by 2, so we're multiplying the x's by 2 and the y's by 1. So that would be a horizontal stretch by a factor of 2. Now think of how you can rewrite the function and then state a vertical scaling that occurred to the parent function. Okay, well, rewrite, what do they mean? Well, what if I cube everything? So that would be y equals x cubed over 8. Or y equals 1 over 8 x cubed. Okay, well, now, think of it as vertical scaling. So I can write this as y divided by 1/8 equals x cubed. Okay, so our scale factor would be 1/1/8, and I would describe this now as a vertical compression by a factor of 1/8. Well, what does that mean? Same question. I did it once as a horizontal scaling and once as a vertical scaling. Well, that emphasizes a really important idea, that a lot of these scalings can be thought in two different ways. If we're looking horizontally, we might say that it's a horizontal stretch by a factor of 2, like in this particular example, whereas someone might look at it vertically and notice that it's a vertical compression by a factor of 1/8. Well, that does make sense that there is some connection here. If we stretched a graph horizontally, and we pulled it left and right, well, we should be compressing it vertically. The graph should be getting closer to the x-axis. And the reason that this is important for us to understand is the next few slides, we're going to be writing the equation from a graph. I might see it one way, you may see it a different way, and they're both correct. Okay, so we have to understand how to check that out. Okay, so write the equation of the graph by identifying the parent function and scale factor. Okay, so the parent function here, we have that V-shaped graph, so it's the absolute value of x. Now, in order to figure out the scaling, I'm going to graph the parent function. So 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2, 2. And I can connect the points, but I don't necessarily need to. So I want to compare these points to the points that I have. So let's look vertically. Well, how can I get this point to this point? Well, 1, 1 to 1, 2, I would multiply the y value by 2. 2, 2 to 2, 4, same thing. So I can think of this as a scaling of 1, 2. So my equation would be y divided by 2 equals the absolute value of x. So y equals 2 times the absolute value of x. So that's think of it as a vertical scaling. Now some of you might have looked at it horizontally. So looking at 2, 2, comparing it to 1, 2, that would be a scaling of 1/2 in the x direction and nothing in the y. So I could think of this as scaling as 1/2, 1. And we would get y equals absolute value of x divided by 1/2. And that would be y equals the absolute value of 2x. So both of these equations are correct. And it's actually pretty easy here. I could rewrite this as absolute value of 2 times the absolute value of x, which is 2 times the absolute value of x. So mathematically, it checks out as well. Next up, so we have a parabolic graph. So our parent function is y equals x squared. So let's see, 0, 0, 1, 1, negative 1, 1. Those are only points. So I can right off the bat see that there's a reflection going on. And let's see, let's compare this point to this point here. So how does 1, 1 become 2, negative 2? Well, I can multiply x by 2 and y by 2. Well, y by negative 2. So I can think of this as a scaling of 2, negative 2. So y divided by negative 2 equals x divided by 2 squared. So that would be y equals negative 2 x over 2 squared. So that's one way. How else can we think of this? Well, let's think. There'd also be a point up here at 2, 4. So how do I get 2, 4 to be 2, negative 2? Well, I can just multiply the y value, right? 2, 4 to be 2, negative 2, so I can scale the y value by negative 1/2. So if I did that, I'd have y divided by negative 1/2 equals x squared. So I'd have y equals negative 1/2 x squared. Now, one thing I want to point out is you don't need to come up with all of these. Your goal is to come up with one of them. I'm just showing you different options that you might come up with. Okay, so either of these is correct. I think those are the two easiest ones, but there are probably others out there that you can find as well. Mathematically, here, just check. If I took negative 2, I'll show you how to check. If I took negative 2 and then x over 2 squared, I can make that negative 2 times x squared over 4, which would become negative 1/2 x squared, which is exactly what we got here. So mathematically, it checks out. Write the equation of the graph by identifying parent function and scale factor. So parent function here is the square root function, so y equals the square root of x. So there we have 0, 0, 1, 1, 2, 4. I can't fit on the graph. So let's see. Comparing 1, 1 to negative 1, 1, seems like the x value's been multiplied by negative 1. So we have y equals the square root of x divided by negative 1. So y equals the square root of negative x. In this case, that's the only one that I see. I don't see another way to define this function. Okay, next, what do we have? We have a parent function of y equals x cubed, the cubic. So we'd have 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2. Let's see, can I get down there? Negative 8. Okay, so I see an easy comparison horizontally. So I'm going to compare 1, 1 to 4, 1. So that's a scaling of 4 on the x, 1 on the y. So y equals x divided by 4 cubed. And that's it. Now, if I wanted to think of it vertically, I think that's a little more challenging. But I can actually figure it out here. If I take x over 4 cubed, I would get x cubed over 64, right? So y equals. So I could also write this as y equals x cubed 1/64 x cubed. So that's a good, really, example to point out the vertical scaling here would be way more challenging to figure out. I don't think I'm going to figure out 1/64 looking at the graph. Some of you may, but not all of you. And the way you would do that, 4, 1, compared to 4, 64, which is the point above it that we can't see, and you'd have to divide by 64 to get that point. Right, so our scale factor would be 1/164 as a vertical scaling. Here, our parent function is y equals the cube root of x. So we have 0, 0, 1, 1, 8, 2, -1, -1, -8, -2 as our parent function. So let's see, comparing vertically, I think that's the easiest. So 1, 1 to 1, 3, that's a scaling of 1, 3. So y over 3 equals the cube root of x. So y equals 3 cube root of x. Now again, we can also think of it as a horizontal scaling. I would take this point 1, 3 and compare it to the point to the right of it, which, let's see, what x value is a cube root of 3? So that would be 27. So thought of horizontally, it would be a scaling of 1/27, 1. So you'd have y equals the cube root of x over 1/27. Y equals the cube root of 27x. And it's actually nice that there are multiple ways. You don't have to think of it one way. You're not stuck. Whatever way you see it, as long as your values are correct and you set it up correctly, you're good. Last question. If the graph of y equals k times f of x, where k is a positive constant, is narrower in comparison to the graph of y equals f of x, and reflected over the x-axis, what must be true about the value of k? So if we rewrite this, we'd have y divided by k equals f of x. Now it tells k is positive. It says narrower in comparison. So that tells me that there's a vertical stretch because the k is acting on the y. So that's why I know it's a vertical scaling as opposed to a horizontal. And then reflected over the x means that k should be negative. Okay, for a vertical stretch, I know that k should be greater than 1. It should be a positive value, multiplying the y values by 2 or 3 or 4, something larger than 1. And to get that reflection, I want to negate the y values. Okay, so that means then that k needs to be some value that's less than -1. Right? Being less than -1 means -2, -3, -4. So if I take away the negative, 2, 3, 4, that gets me my stretch, my vertical stretch, and then the negative part gives me that reflection. Okay, so I'm basically, and then this tells us k is negative. Let's fix that. Okay, so we're basically combining these two ideas to get this inequality to describe the value of k. So here we were working in the opposite direction. We were given the transformation, the scaling, the reflection, or we were given the graph and we had to come up with the equation. Okay, so again, focus on the structure of what the equation should look like, how we set it up, and then putting it in y equals form. So rewatch any parts of the video that you're confused about and then practice with as many questions as you can. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.